and conventional and soft computing methods in SPV system, solar photovoltaic system, and comparison between the P&O and incremental conductance and fuzzy logic MPPT techniques at different weather conditions using MATLAB programming and simulation method. Both methods we are going to discuss today. And modeling and simulation of one practical system whenever we are connecting the PV system to grid connected SPV system by the new method, call it as the extended Lyapunov function. And finally we'll see some results and conclusions and references, and lastly we go to the questionnaire. So what is power quality? Let us see now. The definition of the power quality is that the power quality can be defined as the measure, analysis and improvement of the bus voltage to maintain a sinusoidal waveform at rated voltage and frequency. Different definitions are there, but you can easily understand what is power quality means. This is the power quality to maintain a sinusoidal waveform at rated voltage and frequency at load side. Here in power quality issues, different power quality issues are there. Some disturbances and harmonics and sags, and such major problem is sag and swells. So to overcome these problems, we are using some compensating devices. So before going to discuss all those things here, first of all you need to know what is sag and what is a swell. So the sag is a voltage sag is a short duration. The duration is 0.5 to 60 cycles and decreasing in the RMS voltage magnitude in between 0.1 and 0.9 per unit in RMS voltage, or current at the power frequency for the duration of 0.5 cycle to 1 minute, usually caused by a fault somewhere on the power system voltage sags, are the most important power quality problem facing many industrial customers, especially those with the processor. And what is a swell means? It is an increasing it between the 1.1 per unit to 1.8 per unit as per IEEE standards in RMS voltage or current at the power frequency during from 0.5 to 1 minute. So now we'll see the power system, how these problems are facing. Let us see now. This is the general power quality issues in distribution system. This is a schematic diagram of the power quality problems for end user terminals. So this one is the transmission level, this one is the load, and in between we are having some point of common coupling is there. Here I mentioned some power quality issues. What are there means the effect of system on sensitive loads. Those are voltage sags, swells and unbalances and distortions, voltage distortions. And because of the nonlinear loads in general, the types of the loads are nonlinear loads only. Due to that loads, harmonics are to be created or affected to the system. So that harmonics are the current harmonics, current unbalances, voltage flickers and voltage notchings. So now we will see this is the representation of the power quality issues, how the problems are faced in the power systems because of the harmonics. 32 in between the up to 30% of the level it is affected to the power system, and in voltage sags nearly 25, and voltage unbalances, due to the voltage unbalances it is nearly 20% affected, and because of the swells 15%, and input and voltage transients and others. So this shows the representation how the problem sags or the swells affected to the power systems. So if you want to rectify these problems, we are using some filters like active and passive filters. Let us see here some custom power devices topologies are there. So using of the shunt compensator, series compensator, combination of the shunt and series compensators. Using of the shunt compensator, we can remove the harmonic filtering and reactive power compensation, load balancing and flickering reductions. Using of the series compensation, we can reduce that for voltage sags, swells compensations, and voltage distortion compensation, supply voltage unbalances compensations. Using of the UPQC, both can be compensated by using of the UPQC systems, right? So now we'll see the as per IEEE standards of the power quality categories here. So and so time durations, typical durations. If you see here, sag is occurred 30 cycles in 3 seconds. Swell, it is to be 30 cycles in 3 seconds. Why I am mentioning these two is, I want to concentrating on these two. I want to reduce the sag and swells in the power systems at load side, right? So now, what are the solutions of these power quality issues? So the power quality issues, the solutions are using of the reactive power compensations. So in reactive power compensation, different methods are there to improve the reactive power. One is the synchronous condensers. Again, second one is the mechanically switched capacitors and reactor banks. And third one is the thyristor controlled static VAR compensator and TSC and TCR. And lastly, it is the static synchronous compensation, that is the STATCOM. And if you want to reduce the harmonics in the power system, we prefer passive power filters, active power filters, and combination of these two, that is the hybrid power filters. And if you want to improve the power factor improvement, you are using passive power filters and custom power devices, CPDS, and converter based topologies. Let us see one by one here. In case of the harmonic elimination, using of the passive filters, first figure 1 shows the single tuned, second one shows the double tuned, third one is the second order high pass damped filters. So there is some limitations are there by using of these passive filters. If I am using these passive filters, once it is installed, neither the tuned frequency nor the size of the filter can be changed so easily. The filter can either be switched on or off, thus a step-less control is not possible. So the source impedance, which is not accurately known and strongly influences the filtering characteristics. The changing in the system operating conditions, addition of new compensating devices, and deterioration and temperature effects may increases the designed tolerance, thereby causing the detuning of the filters. So some problems we are facing by using of these passive filters. So we prefer active filters, call it as the custom power devices. In the custom power devices, the family is like this. One is the D-STATCOMs or DVRs or UPQC. So these type of compensating devices are preferred to improve the power quality, right? So we are going to first see the flow chart. Just it is the one power systems what we are going to do there. So power system is there mainly, and after that having generation, transmission, and distribution is there. In the distribution, the main agenda is to improve the power quality here. So what is the amount we need to increase here is the voltage issues and the current issues and cause of the power quality problems. So we are having sag and swell is there. So if you want to reduce or remove these problems, we are using the solution is to use some compensating devices like DPFC, DVR, and filters and STATCOMs and all those things. So if I'm using some STATCOM here, so we can reduce the power, we can reduce that or we can improve the power quality there. So reactive power compensation by using of the STATCOM, and here open loop and closed loop is there. So we are preferring closed loop comparatively to the open loop system. So because the efficiency is to be high comparatively open loop systems. In closed loop system, different methods are there to control the converters in the D-STATCOM. So the different types of controllers are PI controller and fuzzy controllers and INC methods, incremental conduction method, and Petri and observation method. So these are some methods are there, and ANN methods. These methods are there, fuzzy methods are there. Okay. So in my topic, so what is the problems first we are facing in the power systems? First one is here, different control techniques are used for the custom power devices to effectively manage the different power quality issues. and the total THD value is need to maintain up to the IEEE levels, that is below its 5%, and to maintain the objective of the maximum power point tracking by using some algorithms to achieve the fast and accurate tracking performance and minimize the oscillations due to varying weather conditions, and to implement the PWM techniques for shunt active voltage source inverters, which offers the satisfactory current regulation and high efficiency and fast transient responses. The proposed algorithm, so what I am going to discuss with you, that in shunt active filters able to mitigate the voltage and current related power quality issues, and confirmatory results have been presented here. So now first we see the maximum power point tracking by using in the boost converters. So in the PV, that is photovoltaic system, if I am using there, so we prefer boost converter. So to increase the voltage what you are having input from the solar panel, so there we are using some boost converters. So the major disadvantage of in case of by using of the solar module are relatively high manufacturing cost and low efficiency, approximately it is 30%. It is necessary to operate the solar system at the maximum power point under varying environmental conditions. So if I am using so and so PV panels, renewable source, that is a solar energy, the main problem is we don't get the maximum output power from the solar panel. So this is the maximum problem all the people are to be facing there. So we need to maintain we need to bring the maximum power from the solar panel. We prefer some controlling techniques to get the maximum power from the solar system. Okay, so in another one is here we are using DC-DC converters. So how to control the DC-DC converter? What are the control methods are used to get the maximum power or the constant voltage from the DC-DC converters? Let us see now. So by using the linear Kalman filter to get the MPP of the solar PV array had been tracked with an efficiency of 97%, and uncentered Kalman filter technique, then we can get 98.3%. It is the practical value. And here some conventional and soft computing methods are there to get the maximum power from the PV panel. Right, so those methods are, one is the PO method, Petri band observation method. Second one is the incremental conductance method. Third one is the fuzzy logic algorithms. And lastly we'll see the comparison of these three MPPT methods in program as well as the simulation. Right, so in the distribution systems we are using solar energy we are using there. So to get the maximum power from the solar, how it possible means by using of some controlling techniques. The techniques are three techniques I mentioned here. One is the Petri band observation method, another one is incremental conductance, last one is the fuzzy logic method. So here, after getting the power from the panel, so we are using some boost converter. I would like to show you the circuit here. Let us see. This is the MPPT implementations of method 1. So in this particular method, I am not using any controller here. I am not using any controller after MPPT. Just it is directly given to our switch here. What we are using here, IGBTs or MOSFETs, whatever you are using. So we are taking the power from the solar panel. We are taking some two parameters. One is the voltage parameter, another one is the current parameter. Based on these parameters, MPPT is operated here. So after getting this MPPT, we are having some duty cycle is compared to the triangle signal, and this will give the pulses to the switch here. The switch is operated. The type of the circuit is step up type of the circuit, that's a boost converter. So we will get the output voltage is to be improved. Here we are using some capacitors or banks are to be used to maintain voltage as constant, and the diode purpose is to get the unidirectional current flow in the circuit, we are using the diodes. Now here I am not using any controller, I am not using any conventional controller. So if you see the second circuit, if I would like to use some conventional controller, call it as the proportional integral controller, then the output voltage or the pulses are to be controlled by this particular PI controlling technique. So in proportional having some constant and integral having some constant, based on the output requirement, we need to vary the proportional and integral constants, right? So now first we will see some solar panel. So how the output power is varies based on the IV curve, we'll see now. So this is the solar panel what you are having here. The vital importance of these MPPT algorithms of the PV systems are attracted a lot of research on the design and control of these algorithms. And if you see this circuit here, this is a solar panel is directly connected to the load. The type of the load is, let us assume that the resistive type of the load. So from this circuit, I am getting the certain characteristics. If you draw the characteristics between the voltage and current, so I am having these characteristics. So the slope here is 1 by R value. So here it is not reaches to our requirement, that is the maximum power point is not meet at the particular resistive type of the load. So if I am increasing the load from here to here, so see this red line, so I am increasing the load. At that time also the maximum power point is not reached here. So based on the resistive type of the load, how to get the maximum power from the solar panel. So this is the question we are arising here. So how to get the maximum power from these particular panels. So here if I would like to derive the function, that is the duty cycle with respect to this resistance value, then I can meet the particular requirement, that is to get the maximum power from the solar panel, right? So here, to mitigate this problem and raises the efficiency of the solar system, a MPPT algorithm can be used to keep the solar panels operating point at the MPP value, that is the maximum power point value. The maximum power harvesting is performed by adjusting the duty cycle of the DC-DC converter. Duty cycle adjustment is performed with the MPPT algorithm. So I'd like to show you the circuit what you are having here. This is the MPPT control block of the PV system. So we are having so PV system is there, and in between the PV system and DC-DC boost converter, we are using some MPPT controller like our Petri-bend observation or INC method or fuzzy logic method, whatever it may be used there. So finally, we need to derive the expression. It should be in terms of some duty ratio is in terms of the resistance value. So now the duty cycle is related to the input PV cell resistance to the load resistance value. This is our aim to derive the function. So now the equivalent circuit of the PV cell is this. So this is the system. PV system is there. This is your load, and I am using DC-DC boost converter. From the PV cell, we are having output voltage, and load is there, means obviously current will flows there. So now the equivalent resistance is the converter equivalent resistance is R equivalent value. And the boost converter output voltage is equal to V input by 1 by 1 minus D value, where D is the duty ratio. Here if you find out the load resistance value, resistance is output voltage to the output current value, right? So here we need to find this load resistance. The total represented as here the circuit of the MPPT system is equivalent circuit is this input voltage, and we are having the equivalent resistance value. So now the output voltage, boost converter output voltage is equal to input voltage divided by 1 minus D, and output current to the input current value is 1 minus D, and output current in terms of the duty ratio is 1 minus D. From the above equation, we will get output is equal to 1 minus D into input current value. Now by varying the duty cycle, the R equivalent value can be matched with the optimal resistance at which the maximum power will be extracted from the solar system. So now we need to bring or get the maximum power from the panel. Here we need to find out the duty ratio with respect to the equivalent resistance of the panel with respect to the load resistance value. Now if you find out the R equivalent value from here, we need to find the R equivalent value. The R equivalent value is input voltage to the input current value. The input voltage is rewritten as in terms of the output voltage, that is 1 minus D into V output. From this expression, input voltage is equal to V output into 1 minus D value, and the current value I input is equal to I output by 1 minus D. If you simplify this expression, the R equivalent value is equal to 1 minus D whole square into R load value. So from this expression, the duty ratio D can be derived as 1 minus square root of R equivalent by the load resistance value. So here, by varying this load resistance, if the depends upon the load resistance value, the duty ratio changes here. Okay. So if you see one example on it, to draw the maximum power from the PV panel with rating of 125 watts at different loads, then if you see here, this is the graph what you are having for 125 watts. This is the graph. The maximum amount of voltage is 17.3 volts. So see here 17.3, and the current is 7.23 amperes. Then if you calculate it, then we can get the load resistance is equal to 2.4 ohms. Right, 2.4 ohms load resistance value. Now the equivalent resistance of the panel is the load resistance is 5 ohms. So if you calculate it, how much amount of duty cycle or duty ratio is need to maintain in the boost converter means 0.3 value. So this is the calculations what you are having. So here 125 watts solar panel I am taking here. So in this 125 watts, first of all we need to find out the solar panel maximum amount of voltage and currents at maximum peak point. So this is the maximum peak what you are having. That means this is the maximum power point value. That power is 125 watts. At this condition, what is the voltage and current? Find out the resistance value. So that resistance is how much? 17.3 divided by 7.23. We will get 2.4 ohms. That is the panel output resistance value. And what is the load resistance? The load resistance is example, it is equal to 5 ohms. With respect to these two resistance values, what is the duty ratio? So the duty ratio is equal to 0.3. So that means if you maintain 0.3, then it reaches to the maximum power point limits, right? So that is the explanation about by taking one example here. So now we'll see some comparison between the perturb and observation and incremental conductance and the fuzzy logic method one by one. Let us see now, right? So here in the PV method, different types are there: current perturbation method and adaptive control and variable PA method are there. So first see the PV method. So in PV flow chart, if you see this flow chart, so from the solar panel we need to measure two parameters. One is the voltage, another one is the current. So if you see this panel, we need to take two parameters. One is the voltage parameter, another one is the current parameter from the solar panel. So those are the inputs of our controller, right? So those are the inputs of our controller. Now see the flow chart here. So in case of the P and O method flow chart here, first of all measure the two parameters. One is the voltage, another one is the current parameter. So after that find out the power. So the power is equal to voltage into current value. Changing in the voltage is V of k, that is the present value. This one is the previous value, present value and previous value. So after that you need to find out the power, changing in the power. So present power P of k minus 1 is the previous power value. So measure these two values. Here if this is the conditions in case of the P and O flow chart. So if dP is equal to changing in the power is equal to 0, changing in the power is equal to 0, just directly you can return the parameter. And if it is not, dP is not equal to 0, if it is greater than 0, dP and changing in the power and changing in the voltage, both are greater than 0, both are greater than 0, then what should we do there is just increase the reference voltage, just increase the reference voltage, right? If the power is greater than 0 and voltage is also greater than 0, increase the reference voltage. If power is less than 0, if power is less than 0 and voltage is also less than 0, voltage is less than 0, at the time also we need to increase the reference voltage, right? Understand? Here in case of the P and O flow chart method, if the power is greater than 0, changing in the power is greater than 0 and voltage is also greater than 0, increase the reference voltage. At the same time, if the changing in the power is greater than 0 and changing in the voltage is also greater than 0, and what should we do there is, and again you need to increase the reference voltage, right? That means here the conclusion is the changing in the voltage and changing in the power both are either greater than 0 or less than 0. What should we do there is we need to increase the reference voltage. Other than this condition, reduce the reference voltage. Reduce the reference voltage. This is the flow chart for the P and O method. Okay, so it is to be summarized like this. In case of perturbation method, it is positive value and changing in the power is equal to positive. What should we do there is, it is also should be increases. It should be increase. Reference voltage should be increases. If it is negative, perturbation is negative and changing in the power is also negative, what should you do there is the voltage reference value should be positive. That means you need to increase the value. Either these two conditions, first one and second, fourth conditions, whatever it may be, need to reduce the reference voltage. Now we need to take one simulation diagram on this particular concept. So if you see here, the simulation model of the DC-DC boost converter, DC-DC boost converter, having so and so boost converter is there, so which increases the voltage, which increases the so and so voltage. Here the capacitance value is, take it as 330 microfarad. Based on the our output voltage requirement, I have taken here this capacitance value is so and so. So what it is, I would like to tell you, based on our perturbation observation method, in step-by-step method, how it will flows and how the how it is to be constructed. Let us see now, right? So in this particular circuit is to be simulate by using of the MATLAB. We need to simulate this one. So first take the two parameters. One is the voltage parameter, another one is the current parameter. Step by step I would like to explain about this one. So first take these two values and multiply product of these two, we will get the output power. So first read the voltage and current value and calculate the power P of t by multiplying the voltage and current. And third one is call previous value P, and that is nothing but the Pt of t minus 1 and voltage also Vt minus 1 from the memory, and calculate changing in the voltage, calculate the changing in the voltage and changing in the power. This is the changing in the voltage delta V, and need to find out the changing in the power value, right? So calculate this delta V and delta P, and where delta V is equal to delta PV of t minus VPV of t minus 1. This is the previous value, right? Similarly, need to find out the changing in the power. P of t is the present power, P of t minus 1 is the previous power value. So find out these values, and here by using of this sign detectors, you need to find the check the sign of changing in the power and the sign of changing in the voltage. Changing in the voltage. So previously we have seen in this particular slide, if it is positive and positive, we'll get the next perturbation is to be positive. That means we need to increase the reference voltage, right? So here also, while you are constructing the simulation blocks, first of all take the two parameters from the solar panel. One is the current and another one is the voltage parameter, and the product of these two is equal to power. We'll get the power. That power is P of T value, and need to measure P of T minus 1. P of T minus 1. Similarly, need to measure the value of V of T minus 1 value. Right? Find out the changing in the power. Similarly, changing in the voltage value. Right? So now we need to see here the signs of these changing in the powers and the voltages. Right? So if the changing in the power greater than 0, if it is greater than 0 means positive sign. Okay, or otherwise what will happen here, we will get less than, that is else it is less than 0, that means minus 1 value. Similarly here also we need to check greater than 0. If the value is greater than 0 means pass 1. If it is less than 0 means pass minus 1 value. Pass minus 1 value. Now here what should we do there is multiplying the signs, multiplying these two signs. Positive, if both are positive we will get positive, both are negative we will get negative. Even one is negative, the output of this product of this block is negative only. Right. So based on that one, we need to increase the value or we need to reduce the V reference value. Right. So here calculate these two values, then multiplying the result by steps increment value of the duty ratio, that is 0.001. So now if you see here, the increment of the step value is 0.001. Either we need to increase the in steps of 0.001 or we need to reduce the 0.001 based on this product. If this product is positive, we need to increase the value as 0.001. If this product is negative, then we need to reduce the parameter in terms of, that is the voltage reference value is to be reduced by 0.001 to get the maximum peak. Okay, to get the maximum peak value. So the updated value of D is first passed to the saturation block. Need to pass this particular saturation block and pass it to the block to limit the duty cycle to be within the range of 0.1 to 0.9 value. 0.1 to 0.9. It is not reaches to 1 value. It is not reaches to 1 value. If it is reaches to 1 value, 1 by 1 minus 1 is equal to infinity. Output voltage is equal to infinity. From the buck converter, we will get output voltage is infinity. It is not recommended. So it is less than 0.9 only. So the duty ratio is to be varies from 0 to 0.5. It will act as the buck converter. If the duty ratio is varies from 0.5 to 0.9, it will act as the boost converter. So here the operation is to in our buck boost converter operated in between the 0.5 to 0.9 only. Okay, so we need to observe that point also here. So the saturation block output is then passed to the pulse generator to produce the adjustable pulses to drive the switching element of the boost converter. So we can see this. We can also see the output pulses here from the from this measuring block right now. So this is the way you can construct the simulation block by using of MATLAB. In case of P&O method. Now we will see the MPPT tracking in case of incremental conductance algorithm, IC method. So in case of incremental conductance algorithm, so here the flow chart is like this. Start, measure the values of voltage and current, calculate the values of delta V and delta I value. Delta V and delta Y value, that is a changing in the voltage and current values if both are to be in S. So delta V is equal to 0 and changing in the current and changing in the voltage both are equal to zeros. Then we need to calculate here that value is the maximum power and that value is the maximum current value. Otherwise we need to do this like this. No, and delta I is greater than 0. Here D is equal to D plus AD. That is nothing but the changing in the duty ratio value is to be increases here, and and if this condition is not satisfied, then the duty ratio is to be reduces. Here also, here we need to calculate the conductance value, that is 1 by Z, that is the conductance value here. So based on that one, here the flow chart is here. So depends on the flow chart. Again, we need to draw the simulation blocks in the MATLAB. So let us see that one also. Here, this is the simulation diagram what you are having here. First, we need to calculate, or we need to measure the two parameters like P&O method, voltage and current parameters, and call the current values. Call that particular current values I of t-1 and voltage of t-1 previous values from the memory. And after that, calculate the delta V and delta I value. Calculate the delta, that is a changing in the current and changing in the voltage are to be calculated here. To get the incremental conductance, calculate the delta I by delta V value, that is the conductance value what you need to calculate here. So after calculating, the instantaneous conductance is to be calculated. Next, if the changing in the voltage equal to 0, pass the output of control switch 1, else pass the output control of switch 2. These are the control switch 2 and this one is the control switch 1. So you need to pass like this. Here the signal is to be passes here, and the updated value of D is passed through the saturation block before being sent to the pulse generator like your P&O method. So this next slide shows the saturation point. So after that, here we will get some pulses. These pulses are to be given to your boost converter. So the boost converter is operated based on the duty ratio, and the last method is the fuzzy logic method. The fuzzy logic method, using of the fuzzy logic method, here we need to one of the most strong and technique method. This is the extracting of the MPP in the solar system. Fuzzy logic, it is the very robust and works with the impressive and inputs, can handle the non-linearity, no required to have the accurate mathematical model, and relatively simple and design. And here it is the triangular membership function are selected to reduce the computation complexity in this particular fuzzy system, right? Triangular memberships are to be taken here. So here we are having some fuzzification and interfacing engine and defuzzifications. All these are there. These are discussed in the previous session. So I'm not going to discuss much more on these blocks, what it is, and what is fuzzification and interfuzzification system and defuzzification. So here in this particular concept, I have taken 5 by 5 matrix here, 5 by 5 matrix. So the changing error is E represents as error, and delta is the changing in the error, where NB is the negative big and negative small values. So here, based on the this particular particular system here, the fuzzy systems are to be calculated. So for example, one example I can say here, if error value, that is dP by dV value, is NB, let us assume that negative big value, NB is nothing but the negative big value, and NS is the negative small value. N is represents as a negative, P is represents as the positive, S is small, B is big, right? So if error is dP by dV is negative big, and changing in the error is NB, then duty ratio is 0, that is 1. Like that, you need to write the rules in the rule editor in the fuzzy logic MPPT controller, right? So after writing this one, so this is a flow chart of the fuzzy logic. Here also we need to measure the two parameters, voltage and current, and find out the power value. So calculate this error, and based on this error here, the duty ratio is to be changes whether it is increases or reduces. So if it is increases, means we need to it is a closed loop system, it's not the open loop system here we are using. So now if you see the if you go to the simulation, so in the simulation block I will show you the simulation block if by using of the fuzzy system. So read the values of the voltage and current from the PV panel and calculate the power. Here we are calculating the powers, and after that changing in the power and changing in the voltage same as that of the PO and INC methods. So calculate that dP and dV value and divide the dP and dV to obtain the error E of t value, and compare and find out the changing in the error value, that is nothing but delta E. So by using of this fuzzy logic, finally we need to generate that particular pulses which are given to the your buck converter. So depends on the pulses here, the buck converter is to be operated there. Finally you'll get some pulses. So here using the simulation M files, then we can design the total blocks in the by using of MATLAB. So similarly, by using of the programmable method, programming in the MATLAB .m files, we can create the .m files in by using the two controlling techniques. One is the PON method and INC method. I will show you a little bit here. So this is the PNO method. By using of PNO method in MATLAB, we can write the program to get the pulses to operate that one. So here how it will operates, and I would like to show some comparisons with respect to the irradiation effects, and I will show you the three methods. So this is the insolation profile variations, MATLAB output waveforms here. So in between 0 to 0.1 the variations in the solar insolation in terms of the kilowatt per meter squares, and 0.1 to 0.2 the changing in insulations. With respect to this one, if I am using these three methods, one is the POA method and another one is the incremental conductance, and last one is the fuzzy method. Which one is better? Let us see after seeing the next slide. So the insulation levels are to be changes from 0.1 to 0.3, like this 0.6 it is to be increases to 1 value. So now see the next slide here. So if you compare these three waveforms, so one is the theoretical power and another one is the MPPT output power. And another one is IC MPPT method, that is incremental conductance method, and another one is the PO method. So if you see here, comparatively these three methods, fuzzy logic, by using of the fuzzy logic method, we will get the maximum power is to be obtained here. So this is the output power of the PO, IC and FL MPPT methods under the different insulation levels and constant temperatures, right? So here the green line shows the fuzzy logic method. This one is shows the fuzzy logic method. Here we will get the maximum power here. So if you change the temperature variation profiles, if you change the particular temperatures in different time periods, what will happen? See, so in case of the the fuzzy logic gives the better results comparatively to the IC and PO method. So green line shows the fuzzy logic by changing, if you are changing these temperatures. So this is the reference. Let us yellow color is to be reference, the theoretical power value, that is taken as the reference. So using of the fuzzy logic, it reaches to the reference, that is the theoretical power value, right? Comparatively that one. So and it is zoomed here. So we'll get, by using a fuzzy logic, we will get the maximum power is to reaches comparatively other two methods, right? So now the comparison table is this PNO method and IC and fuzzy logic method, how the power and efficiency. Power is 1365 and efficiency is 91%. In case of IC, we will get only 90%. MPPT PO MPPT method 87%. So that means we will get by using FL fuzzy logic, get the maximum efficiency, right? So these are the some values what you are having from the results. So now the last one here we will see some the same PV cells are to be connected to the grid system. How it will varies? Let us see some MATLAB simulation results. Sorry. So some PV based D-STAT by extended the Lyapunov functions. So previously we have seen three methods. One is the P and O method, another one is INC, and third one is fuzzy logic method. In this particular it is single phase system only. This one is the block diagram system layout. So we are using one solar panel. So it is connected to the one buck boost converter. So this boost converter is directly connected to the grid. So we are using so and so load. Type of the load is it is not the linear load. It is non-linear load. So here this Lyapunov function, using of the Lyapunov function, here the converter is to be operates. That means this converter is operates. The boost or converter is operated by using of the incremental conductance method. We know the incremental conductance method, how it will operate, already has seen the block diagrams and calculations. So now the outputs, I would like to discuss about these outputs. So if you see here, these are the results from the previous MATLAB circuit. Okay, simulation circuit. So if you see here, this one is the voltage and currents, all those are to be represented. So there is a phase difference of the current and grid voltage. So if you see here, there is a this is the voltage, grid voltage, and the grid current value. If you see here, the phase difference is 180 degrees. That means the power is feeds to the grid than taking the energy from the grid. Okay. So not only here, the power factor is maintained unity. Even the load is non-linear type, but the current waveform shape is sinusoidal at grid by maintaining the actual bus DC voltage. Okay, so this is the thing happened here. So if you see the second slide, this figure shows the demonstrating the some sudden behavior of the PV inverter currents at non-linear injected type of the load. The sudden change of the PV inverter is analyzed by switching off the loads at 0.4 seconds. This one at 0.4 seconds, and here the power taken by the load is 0. That means here the current is equal to 0, means if you multiply it with the current and voltage, you will get the power is equal to 0. By the grid current is changes to higher value of 0.4 seconds. Because of this total power is integrated to grid. Here not only the current at grid side is maintained sinusoidal, and there is no changing in the DC link voltage. So here the DC link voltage is this one VDC link voltage. It is maintained constant only, even though this to be occurred. The power is at load side is to be equal to 0. We are maintaining the DC link voltage is equal to 0 here. That means it is to be maintained constant, even though power is equal to 0. Right. So now we will see another results what we are having here. Here we can see the irradiation effect is taken from 1000 to 500 watt per meter square. So I would like to change the irradiance from 1000 to 500. 1000, that means I am reducing the irradiance. At this time, the current value is also decreases from 0.5 to 0.55 seconds. 0.5 to 0.55 seconds. If I am increasing the irradiance effect, then it is also reduces. At insulation of solar is reduced, which is connected to the integrated system. The total PV power is fed to AC network system. Even insulation load is to be reduces here. So that means the controller is operated effectively by seeing this, by observing this one, these waveforms. So if you see another observations in this particular circuit, it demonstrates the changing in the insulation from 500 to 1000 watt per meter square. So previous slide is from 1000 to 500 I am reducing the irradiations, that is insulation effects. So now I would like to increase the one from 500 to 1000 watt per meter square. By using this, it is proved that Lyapunov control technique, even we increasing the solar insulations there 0.6 seconds, this one 0.6 seconds, the total current at grid is increases and it is maintained sinusoidal in shape. Not only whenever the insulation of solar 500 watts per meter square, the current at grid is low, where the load at PCC, there is no disturbances effects on the voltage of the PV cell. right? So that means here we can understand our controller is effectively operated. So at this time, if you calculate or if you measure the THD values, so the THD value is 33.96 in case of the harmonic spectrum of the load current. Load current value is always the THD is to be high only, and voltage is 3 point, here see 3.779. It is acceptable according to IEEE standards, and the THD value is in case of this one is 0.06 percentage. This is also acceptable. Okay, so now we'll see some references. These are the some references what I followed. Thank you one and all.
So thank you very much, sir, for clearly explaining about the basic about the power quality issues and MPPT tracking systems in the photovoltaic system and the calculation of correct duty cycle value to get the MPPT tracking by adjusting the R equivalent or R load value, and then MPPT tracking by using the P and O method and incremental conduction method and the soft computing fuzzy logic control method, and the results also showing that it is followed by the IEEE standards. So once again, thank you very much, sir, for accepting our invitation. I request if anybody participants, if you have any doubt, I am giving the permission to unmute yourself. I can ask the question. So participants, I am giving permission to ask any question. If you have any queries about this one, so you can ask now. Okay, if there is no question, we will end the session now, and we will take a 5 minutes break, and at sharply at 3 o'clock, we will start the second session.
Sir, thank
All
you,
the
sir. Thank you very much, sir. If anyone having any doubts on it, just mail me. My mail ID is sampathkumar.papula@becbapatla.ac.in. Thank you, sir. Thank you for
okay, sir.
giving this
Okay, thank you.
Good
opportunity, sir.
afternoon, sir.
Madam,
Good afternoon, sir.
madam, tell me.
Yes.
Hello.
Yes,
Madam.
ma'am. Sorry, ma'am.
Good afternoon, sir.
Good afternoon, ma'am.
Sir, in the perturb and observe method,
Yes.
how should we set the reference voltage, sir?
How should we set?
The reference voltage, V reference.
Reference voltage based on our requirement, we need to place first of all that reference voltage. Let us, if you need to maintain 230 volts, let us. So that one take it as the reference voltage, ma'am.
Which one, sir?
For single phase, we need, if you need to maintain 230, then take that 230 as the reference voltage.
Okay, 230 should be the reference voltage if it is single phase, you are saying, sir?
Yes. Yes, madam.
With reference to the, but we are getting DC from the SV, the solar panels. So I
Yes.
thought it would be related the
Yeah,
DC
it is.
output voltage.
Yes, it is connected to grid system, na. So in grid system, if I am connecting means that is the AC only. So if I want to maintain that voltage to maintain that frequencies and all those, so I'm suggesting you to maintain that 230 volts. In case of the single phase system.
Without grid systems, sir, only connecting to DC converter.
Only
If it is a DC output voltage.
okay.
That depends upon your
Then
load.
how much the big
Madam, at that instant, that depends upon the load requirement, madam.
on the load requirement, sir?
Yes, madam. If you are not connected to grid, then it depends upon only the output of the converter. Okay, the output of the converter, you are connected it as a load. So then that depends upon the load requirement.
Okay. Okay, sir. Thank you.
Okay.
Participants, if there is any other doubts, so please you can ask now. Or otherwise, you can mail that one. So we will end the first session and we will start the second session in 2 minutes. So sharply at 3 o'clock, we will start the second session. So please wait for a while 2 minutes. So thank you, sir. Thank you once
Thank,
again. Thank you very much.
thank you, sir.
Okay, once again, good evening to one and all. It's my pleasure to invite uh, today's other speaker, Dr. K. Kamaladevi Garu. So, Dr. K. Kamaladevi Garu received her MTech degree and PhD from Acharya Nagaji University, Guntur, Andhra Pradesh. She got her PhD degree under the esteemed guidance of Dr. Sheikh Abdul Ghafoor Garu, Associate Professor, Department of Electrical Engineering, IIT Jodhpur. She oftenly visited the IIT Jodhpur recording her PhD work and done some PhD work at IIT Jodhpur under the guidance of the Dr. Sheikh Abdul Ghafoor Garu. At present, she was working as assistant professor in the department of EEE Bapatla Engineering College, Bapatla, since 2008. Her research in the broad area of the protection of distribution network with the penetration of distributed generation in power systems. Dr. K. Kamaladev Garu published a good number of journal papers in referred journals and has good number of the conference publications also in the is her expertise area. On behalf of EEE department, faculty, students, once again, thank you very much, madam, for accepting our invitation to act as a today's resource person. It's time to hand over the session to you, madam. Madam, please continue, madam.
Okay, sir. Thank you. Am I visible?
Yes, madam.
Audible
Yes, yes, madam. Yes, madam. Clearly visible and audible. Please go ahead.
Yes. Good evening, all of you. And it's my privilege to be with you. And once again, I thank the organizing committee to give this opportunity to present my topic. Today, I am going to deal with the protection of distribution network with the renewable energy based distributed generator using wavelet alienation technique. Penetration of distributed generation units in a distribution system are rapidly increasing day by day. Because of so many advantages are there, okay, penetration of distributed generation units in a distribution system are rapidly increasing day by day because of beauty's enormous advantages of DG. And that means it reduces greenhouse, basically it is eco-friendly and reduces greenhouse effects, improves stability of the system, improves the reliability of the system, as well as reduce the power quality issues. So many advantages of distributed generation. That's why day by day we are rapidly increasing the utilization of DG. However, many technical problems are being encountered due to the integration of DG into the utility network, apart from many advantages of DG. Protection issues like islanding and faults are occurred and should be cleared as soon as possible because of these stability of the system may damage. A wavelet transform based alienation technique for the detection of islanding condition faults in a radial fibers distribution system integrated with the four renewable energy, especially wind farm based distributed generators will be discussed here. These are the contents, introduction, methodology, detection of islanding and faults in distribution network with wind model, future scopes. The demand for electricity compel the generating companies to set up small generating plants close to the customers. Before going in depth, so what is distributed generation? We should know what is distributed generation, what is its significance, what are the, that means the utilization of how far we have to utilize this distributed generation and all those things. That means this system of generation is called decentralized or distributed generation. Distributed generation is also known as a decentralized, not centralized. It is a decentralized power generation. DC, this is on-site generation, not from the transmitting energy. Okay, it is on site at that place itself. At that place itself, it generates electricity. On site generation or decentralized generation is a term describing the generation of electricity for use on site rather than transmitting energy or the electric grid from a large centralized facility. The significant distributed generation generally referred to as decentralized source of electric generation. Here, wind, photovoltaic, combined heat and power, and diesel are used in distributed generation. Interconnection of DC system with the grid raises many issues and technical issues. One of the few of those issues are islanding and fault, and so many are there, but I am going to deal with these two issues that are technical issues in which the DC is connected in a distribution system. Few of those issues are island. I am going to deal with this islanding and faults. Before that, what is islanding? It is the condition that the grid is intentionally or accidentally disconnected from distribution system, but the distributed generation continues to feed the local loads. That means the power supply and the power from the grid is disconnected from the system, but still that distributed generators energize the local loads. What are the consequences of that condition? That condition is known as the islanding condition. That means grid is disconnected, that means supply is disconnected, but these distributed generators energize the local loads. What are the consequences when any person is working on that line? That means that means the supply is disconnected. He may think that supply is disconnected. If he is working on that line, but still those distributed generators are energizing the loads, it may become a threat to that person, and it may pose danger to maintenance personnel, public safety, equipment and the distribution system, customers in the distribution system, etc. Moreover, unsynchronized reclosure of the grid to the distribution system may cause damage to the power electronic conditioning equipment of the DC system. Frequency and voltage may not be within permissible limits, which leads to instability in the power system. This system is the best example for the islanding formation in a distributed generation. Here, wind energy is used as a renewable energy based distributed generator. Here, wind energy is used as a distributed generator. Here, synchronous generator, transmission line, and distribution transformer, all things are there. This is all together utility grade. It is by means of a common coupling point, it is connected to a distributed generator. Simply how can we create or how can we simulate islanding condition? Means simply by opening the circuit breaker which is connected at point of common coupling. By opening this circuit breaker, we can simulate islanding condition. That means supply or grid is disconnected from the load, but here distributed generator is energizing the loads, local loads. System, and that means supply is grid is disconnected from the system by opening this circuit breaker, but still this distributed generator energize the local load. This is the best example for the islanding formation. Then another issue is faults. Short circuits and other abnormal conditions occurred in power systems are usually called faults. The fault must be cleared within a fraction of a second. Otherwise, it could extend to the healthy part also, and after some time, the total system may damage, total equipment may damage. Sometimes the total system may shut down. These are the consequences in the event of occurrence of a fault. The voltages, currents, and the frequency of the power system reach abnormal values, affecting the reliability of the supply. Short circuit or ground faults may cause voltage sags or momentary interruptions. That means the power quality issues. The transients of currents are likely to damage the components. Heavy short circuit, that means we know that every fault is associated with the higher magnitudes of the current, transients of the current. A heavy short circuit current may cause a fire, flashovers may occur. Faults on power system also cause sudden changes in power flow in the network, affecting the stability of the system. A sustained severe fault may cause the system to lose its stability. Why? Because stability plays very important criteria in modern power systems. Okay, that means these faults cause lose its stability of the system. And after detection of islanding and faults, what are the advantages? A fast and accurate detection of islanding results to reduce several negative impacts on utility power system and the DC itself, reduce safety hazards to utility worker system and DC itself, reduce PQ related problems. Fast and accurate detection of faults will help in the quick repair of lines and restoration of power supply with the minimum time, reduce occurrence of voltage sags and interruptions. What is the now? Let us define the problem statement. Islanding, faults and PQ disturbances must be properly and effectively detected to mitigate the failing, otherwise it may lead to malfunction and damage of equipments in the power system. This may affect the flow of power in the utility network. Fast and accurate detection of faults will help in reduce total failure of the system. There is a need to propose a technique for the detection of the faults in the power system which can operate the relays in quarter cycles. And much research work has been done in this area. Most of the work is consisting, they can find the detect the faults in half cycle or full cycle, but there is no work in regarding this quarter cycle time period. Okay, that's why there is a need to propose a technique that can operate the relays in quarter cycles to isolate the faulty feeder. Sir, Ravindra sir?
Madam, please continue, madam. Audible, no problem.
Audible. Operate a relays in quarter cycle to isolate the faulty feeder with the minimum time, even in the presence of renewable power generation with the less computational complex. This presentation especially aims at fast and accurate detection of the islanding condition, faults in the electrical power network in the presence of renewable power generation, so that these islanding condition faults may be detected and cleared within quarter cycle time period. Islanding is simulated at a point of common coupling. Okay, it can be created at the point of common coupling, and faults are simulated at each DG bus of the network. That means I am taking 5 bus radial model. One bus is at a point of common coupling and the remaining 4 buses at a DGs, location of the DGs. That means from the point of common coupling, 2 feeder lines, 2 distribution lines. Each distribution line is consisting of 2 renewable wind farm distributed generations. That means 2 feeder lines consisting of 4 DGs. That means 4 buses and 1 bus is at a point of common coupling. Islanding is simulated at point of common coupling and faults are simulated at each DG bus of the network. Here I am using BEC wavelet transform to decompose the current signals to get approximation coefficients, and then alienation coefficients of these approximation decomposition are termed as islanding and fault indices. These indices have been compared with the predetermined threshold to detect islanding condition and faults. Here BEC wavelet transform means I am using this mother wavelet, and wavelet transform basically it is a efficient form to decompose the current signals. Why to decompose these current signals means in order to find the fault precisely and accurately, we have to decompose these current signals. From that decomposed current signals, we get approximation coefficients. From that approximation coefficient, we get correlation coefficients. Anti-correlation coefficients are nothing but alienation coefficients. I am using these alienation coefficients as islanding and fault indices in order to detect this islanding condition as well as the fault condition. Alienation coefficients at each bus over a half cycle window clearly detect islanding and faults. Testing of the proposed algorithm have been carried out for various angles of instance for its more effectiveness. That means at 0 degrees I have found all the results, and 180 degrees I have found, but in between 0 to 180 degrees, 30, 60, 90, 120, 150 degrees, and also I have done all these works, and in order to prove that effectiveness and robustness of this algorithm. Here, let us discuss, let us know few things about wavelet transform techniques. Wavelet means a small wave. Wavelet means a small wave. Convert a signal into a series of wavelets means to split up the signal. Decomposition means splitting up of the signal into a bunch of signals of different frequencies, representing the same signal but all corresponding to different frequency bands, and it is also known as wavelet decomposition. Provide a way for analyzing waveforms bounded in both frequency and time duration. By using these wavelet transforms, we can get the data in both frequency domain and time domain. Wavelet transform, which is a powerful signal analysis tool. This is a very much of a powerful signal analysis tool. Can decompose signal to evaluate the details of objects. The decomposition results involve approximation signal and detailed signal in each level. Before wavelet transform, much work has been done with different transforms like Fourier transform, short-term Fourier transform, discrete Fourier transform, like that. But this wavelet transform is powerful tool. Why? Because in those all techniques we can get either frequency or time domain, but here we can get it. Wavelet transform can provide the data in both frequency and time domain. This is the significance of this wavelet transform technique, and these wavelet transform are having that means detail coefficients and approximations. What is the meaning of detail coefficients? What is the meaning of approximations? Means that means sampling frequency is here. I am taking for example 1000 hertz. This is divided into low frequency component and high frequency components, 0 to 500, 500 to 1000. Again, this high frequency component, both are again divided into high frequency component and a low frequency component. I like that this is the first level of decomposition. Like that, many levels of decomposition. Again, these the frequency is divided into high frequency component and low frequency component. Like that, up to the required level, we can decompose the levels. The high frequency components, all these high frequency components are known as detail coefficients, and the low frequency components are known as approximations. For this work, I have taken the approximation coefficients. We continue like this until we have decomposed the signals to a predefined certain level. Then we have a bunch of signals which actually represent the same signal but all corresponding to different frequency bands. Different frequency corresponding time also we can get. This operation is called decomposition. A set of basic functions called wavelets are used to decompose the signals in various frequency bands which are obtained from a mother wavelet by dilation and translation. Hence, the amplitude and incidence of each frequency can be found precisely. There are many types of wavelets such as Hoare, Dubchis and Samlet, etc. Selection of mother wavelet is based on the type of applications. I have taken these Dubchis wavelet, and this is the best example for decomposition, 4-level analysis of filter bank structure. That means sampling frequency, decomposition level 1, high frequency content, low frequency. Again, high frequency content is divided into high frequency content, low frequency content. Here again, high frequency content is divided into high frequency, low frequency. This is decomposition level 2, decomposition level 3, decomposition level 4. All these high frequency components are known as detail coefficients. All these low frequency components are known as approximations. Depending upon the that means application, some work has been done by taking detailed coefficients for analyzing the faults and then islanding conditions. Here I am taking approximation coefficients. Analyzing the signal in frequency band and a non-uniform division of a frequency domain can be done by wavelet transform, as it utilizes the short window at high frequencies and a long window at low frequencies. It is defined as a series of low pass filter and high pass filter. The scaling and wavelet functions are explained by the following equations. In the proposed algorithm, current signals are sampled over a length of half cycle. Wavelet transform are applied to these samples and analyzed to get required approximation coefficients. Alienation coefficient on the basis of approximation sampling is calculated by alienation coefficients is equal to 1 minus correlation coefficients. RA is the correlation coefficient measured based on approximation coefficients, which can be calculated by using this equation. RA is equal to NS sigma of XA YA minus of sigma XA sigma of YA divided by square root of NS into sigma of XA square minus sigma of XA whole square multiplied with the NS into sigma of YA square minus sigma of YA square. NS is the number of samples per half cycle. XA is the absolute value of the sample set T naught. YA is the absolute values of the samples considering previous moving window of half cycle. The variance between two signals is defined as the alienation coefficient. Its value lies between 0 and 1. Here we can take just 1 minute time to think of deeply. That means here after running the simulation diagram by, that means simulating faults either for unusual condition or any disturbance, whatever it may be, islanding condition either or fault condition. These are and that means these faults, that means islanding condition is simulated by opening the circuit breaker at a point of common coupling. Like that, these faults are simulated at the location of the DGs in the transmission line. Okay, but after completing the simulation, after running that simulation, we can get current signals. Initially, these current signals obtained at each bus were decomposed by using Dobach's wavelet for third level decomposition. I have explained the levels also, first level, second level, third level, like that. Here I am using Dobach's wavelet for third level decomposition with a sampling frequency of 6400 Hz. Like given previous example, 0 to 1000 Hz, like that here in this work I have taken 6400 Hz as a sampling frequency. The approximation coefficients are obtained. That means after getting these current signals, we have applied wavelet transform those current signals in order to get approximation coefficients. After getting these approximation coefficients, get absolute values. Absolute values means that means all are positive values only. After, and that means these current signals, some of the current signals positive, some of negative values. But get the absolute values and all positive values only. The absolute values of approximation coefficients over a current window of a half cycle length are compared with those of a previous window. That means the current window is, and all are positive values only. Every half cycle is consisting of 8 signals only, and that current window is compared with the previous window to compute alienation coefficients. That means here the alienation coefficients are treated as islanding index in case of islanding detection and as fault index in case of a fault detection. The value of alienation coefficients continues to be 0, and that means the current window is compared with the previous window when under normal conditions and without any disturbance or without fault or islanding conditions and healthy condition, the value of alienation coefficients continues to be 0. Why? Because the successive windows contain similar set of approximation coefficients. Why? Because normal conditions. That's why when compare the current window to the previous window, no significant change is there. That's why the alienation coefficients continues to be 0. There is no change in those values. Whereas in the case of disturbances like islanding and fault condition, the approximate coefficient of current window should vary from those of preceding window of similar polarity. Similar polarity. Why? Because we know that that means faults are associated with higher values. Under the disturbances condition, surely there is a lot of difference of the current window variation from those of preceding window of similar polarity. There would be a definite increase in the value of alienation coefficient from 0, which indicates islanding or fault. Islanding, from that we can easily recognize that that is islanding condition or fault condition. Here I am taking 5-bus radial test system. Wavelet based alienation coefficient technique will be used to carry out the proposed study. The brief procedure is following. 5-bus radial test system and 2-terminal feeder will be used to perform the proposed study. This test system will be modified by incorporating the wind to perform the study in the presence of wind energy, and the current voltage signals will be captured at a particular bus of the test system. Captured voltage and current signals will be decomposed to get approximation coefficients by using the wavelet transform. Correlation coefficients, that means the Pearson coefficients. Pearson coefficients were measured based on approximation coefficients, and alienation coefficients were measured from correlation coefficients. Islanding condition, various types of power system faults will be detected and discriminated from each other using the proposed threshold values in the feature plots. This is the single line diagram of the system with the wind based DG. This is a grid transformer, circuit breaker. This is the point of common coupling. 2 feeder lines. Each feeder line is consisting of wind farm distributed generators. Together 4 wind farm distributed generators. This system and 4 wind farm distributed generators are connected to the grid by means of a common coupling point, and transformer 1, 2, 3, 4, 5 transformers are there. These are the distribution lines. This DG1 is located at 30 kilometers far away from the point of common coupling. This is 60 kilometers. That means the distance between the distance from the PCC in between the DGs are that 30 kilometers only. And another, these are the circuit breakers, and 5 loads are there. Major load L1 is connected at a point of common coupling, and L2 at DG1, L3 at DG2, L4 and L5 at correspondingly DG3 and DG4. This is the single line diagram, and these are the specifications of the system. This is the 1000 MVA rated short circuit. Here about the distributed generators. Each distributed generator is consisting of 6 doubly fed induction generator. This wind farm is nothing but 6 doubly fed induction generator, 6 in number. Okay, each of 1.5 megawatts. 1.5 into 6 put together 9 megawatts wind turbines are connected to a 25 kV grid through 30 kilometer 25 kV feeder. Distribution lines are also 30 kilometers each, and the ratings R0, R1, L0, L1 all are given, and the transformer T1, transformer T2 to T5, and the load is L1, and which is connected at a point of common coupling is 15 megawatts 5 MVAR, and the load L2 to L5 is 8 megawatt to 3 MVAR. And that wind energy conversion system is grid data is given like this. Consider in this work frequency 50 hertz and the time period is 0.02 seconds for each cycle. Half cycle means 0.01 seconds, quarter cycle means 0.05 seconds. DC bus voltage regulator gain KP is 8, KI is 400. Grid side converter current regulator gain is KP is 0.83, KI is 5. Speed regulator gain KP is 3, KI is 0.6. Rotor side converter current regulator gain has KP is 0.6, KI is 8. Reactive power and voltage regulator gains are 0.05 and 20. Pitch controller gain KP is 150. This is I have adopted these values for my system, and that means you have to select very carefully this data and the trial and error method. Which data is suitable for your system, you should adopt those parameters only. This is the simulation diagrams. This is the point of common coupling, two feeder lines. This feeder line is consisting of two DGs, wind farm DGs, and this feeder line is consisting of two DGs, wind farm DGs. These are the loads. These are the loads L1 to L5, and this is the L1 load L1 connected at point of common coupling. This is the grid system supply, and this is a circuit breakers. This is a distribution line, 30 kilometers line, pi modal 30 kilometers line, and whenever wind farm distributed generation, the speed will be 15. And the fault is also that means in Simulink library you can get each and every block of this simulation, and 3-phase fault also available. We have this is the islanding for condition. This circuit breaker which is at near to the common coupling point, this we can open this circuit breaker in order to simulate or create islanding condition, as well as fault also we can 3-phase fault block is available in Simulink. We can connect here for each DG. Each DG fault can created at each DG buses. Islanding is created at a common coupling point. These are the simulation results. Okay, after creating or after simulating islanding condition by opening the circuit breaker at common coupling point, okay, if we that means get the current signals and apply the code in order to get approximation coefficients. From those approximation coefficients, get the correlation coefficients, and then and the Pearson coefficient, nothing but Pearson coefficient. Anti-correlation is nothing but alienation coefficients. Okay, that means 1 minus RA square is nothing but alienation coefficients. If you draw that means feature the plot for simple current signals, simple approximation coefficients, as well as the alienation coefficients also. All the graphs are drawn. Please kindly observe. That means it is I have run the simulation diagram for 25 cycles. 25 cycles and a total time period 25 cycles into 0.02. That means 50 has system 1 by 50.02 seconds. 25 cycles means 25 into 0.02. Each cycle comes around 0.02 seconds. 25 cycles total time period is 0.5 seconds. I have introduced this islanding as well as the fault at a 0.4 seconds, and at a 20th cycle. At a 20th cycle, the what is the time period? 0.4 seconds. That means I have introduced, I have simulated that islanding conditions at 20th cycle. That means at a 0.4. That's why we can observe the considerable change in the voltage waveform as well as the current waveform. These are the 3-phase voltage and current signals under islanding condition at a source. At a source means here Here we can get here one scope is there. Here at near the common coupling point at source we get these waveforms, and that means pure sinusoidal waveform voltage, but current I have simulated islanding condition. That means that circuit breaker is opened and disconnected from the grid. Disconnected from the, there is no power supply. That's why from point 4 onwards, straight line interruption of the supply. Here this is at source. Next this is at PCC. PCC also, that means voltage form, the magnitude of the voltage from point 4 onwards decreased, and here disconnected from the power supply interruption. We can indicate these two conditions from voltage waveform and current waveform at PCC. Here these are the simple voltage and current signals at DC location. DGs, how can we get the characteristic curves at DC location? Simply voltage and current signals are like this voltage waveform. The 0.4 onwards decrement is there. Here correspondingly increment is there in the current magnitude. Then this is the approximation coefficients. After simulation we are getting running the simulation, we are getting current signals. For that current signals we have applied that wavelet code, wavelet transformer, in order to get approximation coefficient. If we feature the plot for this approximation coefficients, we get like that 0.4 onwards, there is a change in this waveform also. Then now let us come to that means alienation coefficients. Here these are the alienation coefficients, plots drawn between the time and islanding coefficient, alienation coefficients. All these graphs 0.4 onwards, there is a considerable change. That means transients are and more accurately, precisely we can detect the islanding condition. At this time period 20th cycle, I have simulated islanding condition 0.4 onwards, considerable change is there, transients are taking place. This is at DG1, this is at DG2, 3 and 4. That means here fix one threshold value, trial and error method only. You can fix either 0.4 also very suitable, 0.02 also very suitable. By trial and error we can fix the, that means here only in this case I am taking 0.01 is the threshold value. Above the threshold value, that means these are the above the threshold value which represents the transient, that is islanding condition. Here clearly we can find, clearly we can find 0.4 onwards all DGs are in islanding conditions, gives this type of plots. If we draw between time and alienation coefficients, clearly, precisely, we can find the islanding condition. This is at 50 kilometers. These are at 30 kilometers from PCC. This is 60 kilometers from PCC. This is again D, and that means DG1, DG3 at 30 kilometers, whereas DG3, DG4 are 60 kilometers from point of common coupling. Here I have changed the distance 50 kilometers. I am getting all these waveforms, and the testing of proposed algorithm has been done successfully by varying islanding instance angle. Islanding has been applied at regular intervals of 30 degrees for testing the proposed algorithm. The variation of islanding indexes of three phases is given with the different instance angle. The variation of alienation coefficients of all the three phases were observed as above the threshold value. Here for 30 degrees and for 60 degrees and 90 degrees and 30, 60, 90, 120, 150, 180 degrees. If we draw a plot, all these are above the threshold values, which which indicates eye precise eye detection of eye landing condition. These are the time periods. Corresponding time periods are also we can take from that data. Phase A, B, C, DG1, DG2, DG3, DG4. We can observe all these at 0.003 and before, below the half cycle itself, we can find eye landing condition. Then coming to the fault, this is the flow chart of the fault condition. Detect the fault condition, update half cycle moving window of 3-phase current with the new current sample. First of all, we have to take current signal. From that, we can get by applying the decomposed windowed samples. By applying the code means approximation. In order to get the approximation, we have to decompose these current signals subdivided into many number of. Here 6400 sampling frequency means 6400 by 50, that means 128 samples per cycle. It is sampled or decomposed at the rate of 128 samples per each cycle. Okay, decompose the windowed samples with the Dobach's wavelet to obtain approximate coefficients. I am not touching the detailed coefficients, only I have taken approximate coefficients and low frequency signals only. Then calculate alienation coefficients from the approximation coefficients. Then fault index by averaging the weighted deviation. Here, if a fault index is greater than 0.15, it is the fault condition. Otherwise, it is less than 0.15, it is eye landing condition. Then that means at PCC. Greater than 0.15, this is a fault condition at PCC, whereas greater than 0.4, it is a fault condition at DGs. Then whether it is single, that means single phase fault or a double line fault or a 3-phase fault, we have to consider the number of phases. If NP is a number of phases 1, that is LG fault. If number of phases 2, it is LL fault. If number of phases is 3, LLG fault. LLG fault. Okay. Then here that means again we have to discriminate between LL fault or LLG fault. Here, in order to discriminate a double line fault, whether it is or double line to ground fault, we have to find out 0. That means for another fault index. That means we have to take a fault analyzer here. I will explain in the coming. Okay, simulation of faults has been done after 20 cycles for obtaining post-fault transitions for 5 cycles. The performance of proposed algorithm at various DGs and PCs for different faults at a distance of 30 kilometers from PCC and DGs from each other is demonstrated in the following figures. That means I have that means feature the plots for simple current signals and voltage signals for approximation coefficients as well as the alienation coefficients are also. Here also, as in the case of a previous eye landing condition, here also fault is introduced at the 20th cycle only. 20th cycle only. Total run time is 0.5 seconds. That means I have run the simulation for 25 cycles. At the 20th cycles, I have introduced faults. Okay, here I am simply taking voltage and current signals. See, please, that means observe these waveforms. 0.4 onwards, voltage signals, the magnitude of voltage is decreased as well as transients are taking place in single phase. That is nothing but R phase or nothing but A phase. That's why variation of voltage and current signals of AG fault at DG1. Why? Because in phase A only we are observing considerable change, that is transients. Clearly we can observe the approx, that means the corresponding voltage magnitude is decreased and the transient is taking place in the current. Okay, again approximation coefficients are also single phase we are having considerable change and transient lot of change is taking place. That is also AG field. In A phase only we are getting that change. Okay, this is at DG1. Approximation here we can observe the change in two phases. Those are in C phase and A phase, and the faults are occurred in these both phases. That's why transients are taking place in these two phases. This whereas B phase, ABC phases low, A phase is under the fault condition and fault is occurred in C phase, whereas B phase is a healthy condition. That's why the waveform is like that. This is a healthy condition. Okay, this is a fault condition. These are about the approximation coefficient. Whereas to detect more precisely and clearly, we have to go for alienation coefficients only. Here, these are the graphs of alienation coefficients. Easily we can find out. Found here also we have to fix the threshold, one threshold value. Here threshold value for PCC. Of course, whenever we introduce fault at disease, there is a change, there is a lot of change in the current signals and voltage signals at corresponding PCC also. AG, if we introduce AG fault at DG at PCC, like BG fault at PCC, BG fault at DG1 at PCC, like that AG fault at DG2 corresponding PCC also, like corresponding waveform at PCC also. Like that I have retrieved all the waveforms at corresponding DGs as well as PCC also. For all the graphs which are getting at PCs, I have fixed threshold value as 0.15. And for all the graphs which are retrieved at DGs, I am fixing threshold value at 0.4. How can we get these threshold values? Means we have to decide that threshold value in such a way that faulty phase should be higher than that value and healthy phase should be lower that threshold value. That is a powerful symbol. That means higher than the threshold value is the faulty phase, and below the threshold value those phases are healthy phases. And that means your threshold value should be above the maximum point of healthy phases and below the maximum point of faulty phase. Remember that your threshold value should be above the maximum point of the faulty maximum point of the healthy phases, as well as below the maximum point of faulty phases. Here take this is the only one transient is taking place. This is A phase, red is B, and green is for C. Here in blue line, that means in A phase, lot of changes occurred, transients are taking place, which is above the threshold value 0.4. Easily we can say that is AG fault. The fault transient is taking place in A phase. That's why this is AG fault. Remaining B and C are red line and green line, and that means these are the healthy phases below the threshold value. And the corresponding graphs at PCs, of course, we have introduced the fault, we have connected the fault at DGs only, but there is a change taking place at PCs also. It affects the values at PCC also. That's why I have to retrieve the values at PCC and feature the plot. Here 0.15 is the that means threshold value. Healthy phase is under the threshold value. Faulty phase is above the. Here also two phases. That means here C phase and A phase. Fault occurred in both these, and line to line, either line to line or LLG. It may be LLG or it may LL also. But clearly we can say fault occurred in these two phases, and this red and B phase is a healthy phase, and corresponding waveform at a PCC also, that means the faulty phase is below the threshold, and sorry, healthy phase is below the threshold value, and healthy faulty phases are above the threshold value. This is at DG1 and at PCC. PCC. The above figure shows variation of fault indexes of three-phase currents with the time at DG1 and PCC. It has been observed that the fault index of phase A is greater than the threshold, and for those of phase B and phase C are lower than threshold value. Like that, we can for ABC. This is at DG2. I am giving here BC. These BC faults are above the threshold value, and A phase is below the threshold value, and that means A phase is a healthy phase, and fault occurred in two phases B and C. Like that, corresponding waveform at PCC. Here also A, B, C, G fault, and three phases are above the threshold value, and corresponding waveform at PCC. These are at DZ2. Here also by seeing itself we can say that here only single phase, that means the B phase, fault occurred in B phase, remaining two phases are below the threshold value, that means healthy phases. Like that here also, that means A and B, AB fault, either AB fault or ABG fault. How can differentiate or discriminate line to line or double line to ground fault also? I will say here clearly this is ABG fault corresponding graph from at a PCC also. This is at DG3. Like that here at DG4, it was observed that fault index of phase B is greater than the threshold value, whereas fault index of phase A and phase C are lower than the threshold value, which is evident that a fault is a line to ground fault at DG3 and PCC. Like that here also at DG4, by seeing itself we can say this is BCG fault. At DG4, CG fault at DG4 and at PCC. Here also BC fault at DG4 and PCC. Like that easily we can say and discriminate also. These are the AC fault at PCC and AB fault at PCC. And discrimination, let us see how can we discriminate whether it is LL fault or LLG fault. Why? Because in both the faults two phases involved. By seeing itself you can't discriminate whether it is LL or LLG. But in graphs we can find the transient, in which phases the transient is taking place. By seeing itself easily we can say transients are taking place in these two phases. That's why it is LLG. Whether LLG, that means fault index alone, we can't judge that condition to discriminate between AB and ABG fault or LL double line fault or double line to ground fault. Zero sequence currents are required. That means in order to get these zero sequence currents, we have to find ground fault threshold. That means zero sequence ante sequence analyzer block is available at a Simulink library. Sequence analyzer, three options are there: positive sequence, negative sequence, zero sequence. By selecting zero sequence for that sequence analyzer, get the values of ground fault threshold. If ground fault threshold is equal to 1, it is enough to discriminate LLG from LL fault. That means if we plot graph for these values, see this graph. After featuring the plot for these, and this is the threshold value of zero sequence currents and ABG fault and AB fault. ABG is red line above the threshold value. AB fault is just below the threshold value. By just featuring the plot for zero sequence currents, easily we can get easily we can discriminate or differentiate double line to ground or double line fault. Next, different for different incidence angles also, 30 degrees, 60, 90, 120, 150, 180, for all these degrees, and that means corresponding time period may be changed. That means then they click the right signal and fill the data. While filling that data, put 30 degrees, 60 degrees, 90 degrees, like that. AB fault at DG1, ABCG fault, and we can observe in all these cases, all these values are above the threshold value 0.4. Above the threshold value 0.4. It is evident that all these are faulty phases. Okay, this is the time information of the regarding time period in which that a fault can be detected. See, observe fault AG fault in A phase. Phase A, it is taking place. Phase B, no. Phase C, no. That means AG fault. Detection time, at which the that means phase crosses the threshold value. At which time the phase, that particular phase, AG phase and A phase, BCG and both B and C phases crosses the threshold value. We have to take, and crosses the threshold value means it is evident that it is faulty phase. That means a fault condition can be detected at that time period. Corresponding time period, if you take, those are like this: AG 0.0025, BCG 0.0025. We can detect a fault in this time period itself, 0.0025, 0.0025. Like that, AG, BCG, CA, ABCG, for all types of 11 types of faults, we can tabulate the time periods also, corresponding time periods also at all DGs as well as point of common coupling also. From these, we can observe that all the time periods are less than the quarter cycle. That means 50 Hertz system, time period is 1 by 50, 0.02 seconds for one cycle, and 0.01 for half cycle, 0.05 is for quarter cycle. If we observe these time periods within the quarter cycle, we can detect the faults very accurately and precisely at DG4, at DG3, at DG2. I have to tabulate all the time periods. Those are like this. It is evident that all the faults can be detected within the quarter cycle. When compared to other works, that means so much of research work has been done in this area, and that means in protection. That means to detect and locate the faults, as well as to detect the islanding condition. Passive methods are there, active methods are there. So many methods are there. Here wavelets ANN detection, ANN is used for location. Here detailed coefficients are taken there, but it can be detected in half cycle. If we observe all the techniques, all these are, that means in half cycle only the faults as well as that means islanding condition are detected. But here wavelet based alienation technique, by using these current signals, by decomposing these current signals, by getting approximations, run that approximations alienation, if we plot the figures, easily we can find within the quarter cycle itself, we can detect the fault and islanding condition. These are the about. We can replace that wind farm DGs with the PV cells also, photovoltaic cells also. Again, hybrid model also we can detect. That means 2 or wind farm, to our photovoltaics as well as with the restart cam. Also we can do it. Though all those are the for future scope of this work. Thank you so much. Once again, I thank organizing committee for giving this opportunity. Thank you so much.
Thank you very much, madam, for giving the clear cut about the faults and its consequences, importance of the stability in modern day stability systems, protection of the distribution network with renewable energy based distributed generation using the wavelet annihilation technique, and showing the results by inserting the different faults, and also clearly explain about the discrimination between the LL and LLG faults, and how to detect and locate the faults in the modern day system, and also giving the clear cut about that wavelet technique is very useful to identify the fault in quarter cycle itself. Then the other techniques are able to locate the fault in the half cycle, but this technique is very helpful. So I hope all the participants are very happy with this presentation. And I unmute, I given the permission to unmute all participants. If anybody have any queries regarding this one, please ask now the resource person. So participants, if anybody have any questions, so please let me know. We will discuss on that one.
Sir,
Madam.
good afternoon, ma'am. This one you have done MATLAB program or what, ma'am?
Yes,
Like,
ma'am.
means the aim is how to locate the fault location, ma'am. Like
Fault location in the distribution line, madam, near to the DG.
Thank you, ma'am.
Any point in between that load point and DG, so that distribution lines is there, na? At that you can locate. You can install.
Participant, if any doubt is there, please unmute yourself and please ask the resource person. Otherwise, we will end the session now. Once again, thank you very much, madam, for accepting our invitation to access it today's resource person and presenting your valuable research in the field of the protection of the power system area. So once again, thank you very much, madam. And dear participants, I shared the feedback form in the chat box itself. All of you, please fill the feedback. And please note that one participation, feedback, submission all days is necessary to get the certificate. So certificate is not a important thing as we know that one, but you need to listen the all the sessions and to get the some knowledge in the field of the electrical systems. Okay, once again, thank you one and all. Thank you very much for accepting. Now I am ending the session. Thank you.